Welcome to this explainer. Today, we're doing something really cool. We're going to act as mathematical translators to decode something truly magnificent. We're looking at exactly how the Adelic Langlands Program proves the Bass Conjecture. And it does this by hunting down a vanishing trace through global anomaly cancellation. It's basically a profound mathematical detective story, and we're going to follow the evidence right through the equations. Let's dive in.
Here is our roadmap for tackling this dense proof. It's a multi-lens tutorial. We'll start with the Bass Conjecture blueprint, then move down into the local p-adic sector, unpack things by unrolling the determinant, zoom out with the Selberg Trace Formula, and finally, bring it all home with the Grothendieck Riemann translation.
All right, let's jump straight into part 1, the Bass Conjecture blueprint.
The central mystery we're unraveling boils down to this single, incredibly elegant equation. The Bass Conjecture asserts that for any element G of infinite order within a finitely generated group, the trace, represented here by capital T little r, of its action over the integral group ring must evaluate to exactly 0. But, why does this matter? And how do we rigorously prove that absolutely nothing is left behind?
Well, let's break down these variables. An infinite order element, our G, creates a non-terminating trajectory. It just goes on forever. So, asserting that this trace is erased means the structural finiteness of linear representations actually forces the trace to vanish. This is a massive deal, because a non-terminating trajectory threatens the underlying math. Topologically speaking, erasing this trace ensures that the Hattori-Stallings rank behaves predictably and that the Euler characteristic of a group can be localized arithmetically. If this trace wasn't 0, our topological math would quite literally start tearing at the seams.
So rather than staying trapped in discrete algebra, the framework does something brilliant. It maps that infinite trajectory directly downward. We're translating the problem to a place where we can actually solve it. We move from the infinite order element down through the group ring mapping geometrically onto the Hecke eigensheaf, and finally resting on the nilpotent unipotent monodromy lines of a global automorphic representation, and that yields our local Langlands parameters.
Which brings us to part 2, the local p-adic sector.
Here's the catch. Because an infinite order trajectory cannot be neatly diagonalized into simple roots of unity, it gets forced into a non-trivial parabolic matrix assignment. In this matrix, rho of G, our semi-simple component, is just the identity matrix, but our off-diagonal variable, delta sub p, represents our arithmetic translation parameter. Now, if this trace didn't equal 0, this off-diagonal parameter would act as a wildly ramified topological charge. It would cause our local Swan conductor to diverge exponentially, which is exactly what we don't want.
So let's see how we fix that in part 3, unrolling the determinant.
Okay, the pressure is on. How do we evaluate the trace of this parabolic matrix to prove it evaluates to exactly 0? We follow a highly specific 3-step mathematical process. First, we define a square zero nilpotent monodromy operator. Second, we unroll the characteristic polynomial of that determinant. And third, we isolate the explicit parabolic local component.
Let's actually look at the math for these steps. In step 1, taking the logarithm of our parabolic matrix yields our monodromy operator, n sub g. This is a square zero nilpotent operator, meaning if you square it, you get a matrix of pure zeros. Moving to step 2, and this is the magical part, when we take the determinant of the unramified Frobenius action, watch how the characteristic polynomial collapses. That off-diagonal parameter, delta sub p, it completely vanishes from the final equation. That leaves us with step 3, an explicit local factor of 1 minus p to the negative s, all to the power of negative 2. It is completely unramified, with 0 Swan conductor penalty terms.
To really appreciate this, let's put classical math head-to-head with this derived framework. On the classical side, if we take the standard matrix trace of our parabolic matrix, 1 plus 1 equals 2. It leaves a residue of 2. But on the derived automorphic trace side, within Lagos field theory, we look at the variation of the trace along continuous loops. This forces the trace to 0 identically. It's driven by the commutator relationship, where the commutator of the step-up operator h and n sub g yields exactly 2 n sub g.
So why does the derived trace vanish while the classical one doesn't? Well, the continuous weight shifts of the SL2C algebra dynamically absorb that off-diagonal mass, delta sub p. Think of it like this. The horizontal slice of the Hecke eigensheaf effectively shields our ground state from all that infinite cyclic chaos that element G was trying to introduce. It just eats it right up.
Now let's zoom out for Part 4, the Selberg Trace Formula.
Having successfully erased the trace locally, we need to look at our global analytic lens to see the bigger picture. And this brings us to a massive structural concept, the Universal Cosmic Partition Function. Now, this isn't just a simple formula. It's a macro-level, global automorphic function that tracks the fundamental structural invariances of our entire mathematical universe. It actively enforces an absolute scale inversion symmetry across the whole Adel ring.
Integrating our local matrix into this global picture requires a big shift, moving from the geometric side of conjugacy over to the spectral side of automorphic states. During this transition, which is often called the melting regime, the geometric input of our unipotent orbital integral literally melts through Arthur's truncation parameter, capital T. It resolves the boundary divergence perfectly and flows right into the continuous scattering waves running along the Bruhat-Tits tree.
Take a close look at this direct spectral mapping law. The left side of the equation represents the geometric residue. That's the untruncated volume of our infinite order element. On the right, the integral contains the logarithmic derivative of our cosmic partition function, which gives us our phase readout. Because we've embedded our trace erasure operator into this integral, shifting the trace strictly off diagonal, it mathematically guarantees that the continuous spectrum's coupling to the specific unipotent orbital profile vanishes completely.
Now let's play devil's advocate for a second. What happens if the math breaks down? If the trace were not zero, it would create a massive instability. It would fundamentally destroy the automorphic invariance of the L function, basically breaking the absolute character of the universe's mathematical rules. So, the universal arithmetic coordinator dynamically quenches the parabolic mass to prevent these catastrophic mathematical paradoxes. It absolutely forces the trace to be zero just to keep the whole system stable.
Finally, our last stop, Part 5, the Grothendieck-Riemann-Roch translation. Topologically speaking, our infinite trajectory forms a non-terminating cylinder. Because G has infinite order, it can't close onto a compact cycle, which means it carries zero discrete topological charges. During translation, its arithmetic churn character collapses beautifully into a pure localized Green's current, little g subscript y sub g on the complex manifold. When we apply the proper push-forward, pi star, it reduces entirely to evaluating differential currents over complex fibers.
To conceptualize the math that follows, I want you to think about this physical analogy. Imagine continuous waves running to infinity. They generate perfectly symmetric destructive interference, resulting in exact analytic erasure. The trajectory is essentially canceling itself out by reflecting perfectly against its own infinite nature.
And that symmetric, destructive interference? It is mechanically captured by the regularized Quillen metric h sub q. When we evaluate the integral of the natural log of lambda squared d lambda from negative to positive infinity, it evaluates precisely to zero. The spectral zeta function behaves as a non-compact scattering profile. It completely absorbs the analytic torsion so that the degree 1 arithmetic class of the push-forward is forced to evaluate to exactly zero.
So what is the ultimate physical takeaway here for the sector 1 spacetime baseline? Looking at the effective metric equation, because that pushed-forward arithmetic class zeroes out entirely, the infinite cyclic trajectory injects zero net mass and zero local stress energy anomalies into the background metric. The geometric distortion is exactly zero. This means classical test particles on gravitational geodesics remain completely unperturbed. The vanishing trace is just the exact algebraic mirror of this geometric erasure. Bringing it all together, synthesizing this triad of proofs. Whether we look through the algebraic local lens where weight shifts absorb mass, the analytic global lens where the functional equation quenches volume, or the topological geometric lens where the Quillen metric ensures destructive interference, the arithmetic books balance perfectly. The universe's mathematical source code automatically quenches the traces of infinite trajectories to preserve the absolute smoothness of emergent spacetime. Which leaves us with a pretty wild, provocative thought. If the mathematical source code of reality has these built-in absolute safeguards to automatically quench infinite trajectories and maintain a perfectly smooth spacetime baseline, what other structural anomalies is our spacetime actively hiding from us? It really invites us to look even deeper into the cosmos' mathematical architecture. Thank you so much for exploring this complex proof with me.